The next part of circles that we're going to take a look at are their chords. And so we have 4 different theorems that we're going to take a look at. And we'll start with the first one. So the first one says that in the same or congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So let's go ahead and take a look at this. Let's draw a circle to look at. That's not very good. It's probably going to be worse though. Okay. So 2 minor arcs are congruent if and only if their corresponding chords are congruent. This is probably the most straightforward of my theorems I'm going to take a look at. But it's saying that if I have 2 chords, and they have the same length and they're in the same circle or congruent circles, then what has to be the case is that the arcs that they form are going to be congruent to each other as well. And this is a biconditional statement too. It says that if then the arcs are congruent, then the chords that create them have to be congruent as well. This is most straightforward. Makes sense that if I have a circle that has 2 chords, or rather 2 circles that are congruent to each other, that have 2 chords in them that are congruent to each other as well, then the arcs that they create will be congruent and vice versa. So not a lot to say here. It's pretty straightforward. Let's take a look at the next one. So here are 2 more that they're kind of converses of each other, but not exactly. And so they have to do with circles and chords that are perpendicularly bisecting each other. So if the first one says that if one chord is perpendicular bisector of another chord, then the first chord is a diameter. So if I have a circle, again, and in here I have a chord. Here's my chord. If I were to find the perpendicular bisector of this segment, so let's just go ahead and do this color. So if I find the center, it's going to be about here, or the midpoint, and then I were to draw in the perpendicular bisector of that chord, what this has to be is a diameter. It has to go through my center, which I feel like should make intuitive sense to us, because if I'm dividing this arc in half because I'm bisecting this chord, I'm also bisecting the major arc as well. I'm bisecting both of these arcs, and so what I'm getting on each side are 2 sets of arcs that sum to be the same thing, and so they're both semicircles. And so whenever I have a chord that is bisected perpendicularly by a segment, that segment has to be, or by a chord, that chord has to be a diameter. This next statement is kind of the converse of it. So then if I have a diameter of a circle and it's perpendicular to a chord, so I'm going the other direction. So if I have a circle, so draw my circle again, and I have a, let's see, so if a diameter of a circle is perpendicular to a chord, so I need a chord. So if I have a chord, and I have a, let's see, and the diameter bisects, oh, sorry, no, I started in the wrong spot. The diameter of the circle is perpendicular to a chord, so if I have, it has to be perpendicular. Poorly drawn. It has to be perpendicular. Then the only way that it can be perpendicular to this point, or to this chord, is if it bisects it, so it divides into congruent parts. Which also makes sense to us because if I'm talking about from the center and I'm trying to find the closest point to this chord, it's always going to be this perpendicular point, of which this point on my chord is the one that is closest to the center, all right, then my bisector. So these are kind of converse to each other, not exactly, where I'm just moving in different directions. The first one, I know that if one chord is a perpendicular bisector, then it has to be a diameter. And this one says that if the diameter is perpendicular to a chord, then it has to bisect it. The alternative statement, and maybe I should think more about this before I say it, but is also that if a diameter bisects a chord, then it's going to be perpendicular to it as well. And so it's just a matter of we're starting with knowing that if the chord is the diameter or not. Yeah. So these two kind of go together with these chords or diameters being perpendicular bisectors of another chord. All right, so that was 2 and 3, and now we just have one more to look at, which is this. In the same or congruent circles, two chords are congruent if and only if they are equidistant from the center. So this is also another one that I feel like is going to be intuitive here, where so if I have a circle, and in here then I have a chord. So when I talk about the distance from the center, I'm talking about, once again, this perpendicular distance. And then I have another chord over here, All this obviously not to scale because I'm bad at drawing. And I talk about this distance as well. If they are the same distance away from my center, these two chords have to be congruent. And vice versa. If I have two chords that are congruent to each other, they have to be the same distance away from the center of my circle, which is fairly intuitive from the standpoint that any point that or just the chords in general have to be the same distance away, no matter how I kind of like rotate them around the circle, because really I could just rotate the circle around and get the chord in the same spot as the other one, so the distance have to be the same as well. So again, this is a biconditional, saying that if I know the length of the chord and it's congruent to another one, then it has to be the same distance, and if the same distance, or if chords are the same distance from the center, then those chords have to be congruent as well. So those are 4 theorems that I can use that honestly aren't that interesting in and of themselves, but we're going to use them now to solve a whole bunch of different problems and find some lengths of chords and circles.